it's quite a challenge to follow John, definitely, and quite impressive. Lots of, and not only scientifically but also practically, lots of advances and applications truly impact the world. In fact, the work I'm talking about actually somehow inspired, really in the early days of collaboration and also on-off collaboration with John over the years as well. On focus on photonic crystal structural optics side. So the title of my talk is Photonic Crystal Membrane Cavities for Optical Sensing and Gas Analysis. And this work is primarily in collaboration with Professor, my colleague here, Alice Sang at the University of Texas, Arlington. So, okay, without further much introduction, you all very well know from Professor John Rogers' work in early days and how we can make those rigid structure into a flexible structure. For example, different kind of inorganic silicon semiconductor materials where you can make it a curved or flexible structure. And I like this cartoon from his group website. You can find more information where he is also advancing. I just heard a snapshot of what his latest advance, but really over the years, lots of inspiring pioneer work of different kind of flexible devices. As you heard, excellent talk just now. And some of the work I believe is summarized some in books already on silicon nanomembranes. Also, my another collaborator, Professor Zhenqiang Ma from University of Wisconsin, talk about inorganic flexible optoelectronics, where we have some chapters contributed to those papers, books. So what are we talking today here is so start with a brief overview, look into really the unique capabilities we are developing by combining nanomembrane technology with photonic crystal cavity structures to develop different kind of devices, so-called photonic crystal membrane photonics. And then I will spend half of my time looking to recent work on really optical sensing, especially focus on gas analyzer on the chip. Some progress we are making and still ongoing progress. Some recent advances, and finally a few brief slides on beam control to be able to forming integrated optical system where you have sources, you have detectors, you have sensing element, and also you have of course beam control where those phase control and the meta lens structures would be essential for this application. And they will conclude. So the basic structure we have been working on has been well known now, called photonic crystal structure, is inspired by the butterfly wings, especially looking to so-called light coupling from free space, so-called surface normal operation here. You can see where we created this periodic modulated refractive index structure, for example, by drilling holes in the silicon or some other dielectric materials. You can see some of the structures we made in the years. And if you design right, you can have total 100% reflection or total 100% transmission by designing properly the lattice structure and the index of the structure. So this kind of material system have actually a few different unique capabilities or features optically. You can achieve really very narrow optical filter where you have a very high Q filter, especially if you want to have a narrow band passing structure, either for reflection and transmission. Or you can have a broadband reflector where you can replace the conventional multi-layer DBR structure to have a very compact reflector, dielectric reflector. And also we talk about also field enhanced absorption property as well. So those three different elements you can see later on, we can build independently and eventually can be evolved to be a stacked as an integrated optical sensor system. That's kind of our long-term vision. So as I mentioned, with this integration of photonic crystal structure and the nanomembrane, we looked into heterogeneous integration. For example, a laser on silicon structure where we have a two single layer photonic crystal cavity with a 3-5, in this case, gay media sandwiched in between to form a semiconductor surface emitting laser, a VCSEL type of structure here. Could be very compact, a few micrometers thick. we could also make a very high Q, potentially infinite Q cavity by using single layer or multi-layer photonic crystal cavity structures. Or of course, we can make a flexible optical filter as well. So just a quick overview, a few of these properties here. For example, based on this narrow spectral band or high Q structures, we can make a flexible filter with a reasonably high Q factor, narrow structural band, which can be built either on glass or on a flexible polymer substrate here. Or we can stack, actually, in this case, by control this bi-layer structure here. You can see that's some schematic and also an SM image showing this two-layer of crystal silicon based on a multi-layer stacking transfer printing process pioneered by Professor John Rogers, where we can be able to actually precisely control the lattice offset of these two layers, so we can, in principle, achieve infinite Q. So in some cases where if the Q factor, as you can see, sort of for sensing or some kind of optical design for AR, VR, where those Q factor engineering is critically important. In this case, we can leverage this bi-layer structure based on a stacking process to achieve very high Q here. The second aspect based on this photonic crystal structure, where we can have so-called perfect absorption, meaning now you don't need a very thick layer. Especially, it's very important for wearable, for bio-integrated structures, where film thickness probably is one of the limitations in some cases to get into this flexible and also thin film factor platform. Here, example we have here is a thin layer graphene. Typically, you can only absorb 2.3% absorption of the light. By couple this into a silicon, single layer silicon structure, and on a glass substrate or any polymer substrate or flexible substrate. In this case, if we design right, you can see some SM image and also a micrograph of this structure here. What we was able to achieve actually, without any other complication, we can achieve in principle 50% of absorption from this monolayer structure, very compact structure. And experimentally we demonstrated for this particular design about 38%. And if we adding a reflector on the backside here, and in principle we get 100% absorption, and then we experimentally demonstrated close to 90% absorption. So this could be potentially utilized for spectral dependent detectors or high performance detectors. If we care about a signal noise ratio, if we care about really only single wavelengths, or sometimes you may want to tuning the wavelengths. So those things can be considered as a kind of interesting detector scheme here, based on this principle here. And lastly, we also looked into the broadband reflector here. Okay, it's very thin, like in this case, a 340 nanometer thick silicon. We could get 100% reflection. And we build on silicon. We also build on glass substrate. You can see here, there's some of the works also collaboration with John as well, where we can achieve really a very high performance reflector with a very thin platform. And you can imagine also can be flexible. And with that, we was able to making different kind of active devices, lasers. For example, we was able to demonstrating a very thin, there's a few micron thick laser structure, surface emitting laser structure, based on this reflector property, and later on using this cavity property of photonic crystal cavity, slightly different design, we can achieve even thinner structure where you just need a one layer of photonic crystal cavity, where you can achieve really high performance lasers, and some of them can be very high power. So that's kind of a few applications on the photonic crystal side for sensing platforms. And then this just a one slide highlight some of the recent work collaborated with John's group on bioresorbable optical sensor system for monitoring intracranial pressure and the temperature, where the key here is really very challenging. Actually, the fabrication process was developed by John's group actually here, looking to two kind of platform. One is a fiber cavity structure, One is a photonic crystal cavity structure or embedded, and we can do pressure sensing measurement. You can see one of the key difference here. You can see the sensitivity is very different here. You can see depending on the design and the range of detection and the sensitivity, you can choose use a fibro cavity, or especially you want to look into relatively large range of pressure range, and or if you need a very high sensitivity measurement, then you can look into photonic crystal cavity, where you can have a very sensitive tuning of this resonance here. So those some of the work already published already a few years ago on this. So that's kind of give you a really kind of first part of background introduction about this photonic crystal platform we have been using with a goal. Of course, there are different applications we're looking to for in different aspect for datacom applications, for telecom, and also one of the really key area we are kind of get more and more interested is this sensing platform. That's especially this part of gas analyzer work in collaboration with my colleague, Professor Sang here. So one of the challenge issues for optical sensing, or especially gas sensing in general, is the specificity. How you can be able to monitor multiple gases to be able to separate them out, right? So, and in chemistry, of course, this is well-known lab instrumentation, gas chromatography. Okay, so basically the idea here is you have a gas, going through this long column coated with polymer, and the gas going through the polymer have a different kind of basically separated by this long column here. So you can measure time-dependent spectrum here, and then by calibration you can know each of the peaks corresponding to each of the gases in a system. It's very powerful. The only challenge here, of course, is too big to bulk. So our vision has been looking to, can we scale, shrink, right? There are lots of work already done, especially on the MEMS, some other things, looking to how to shrink and the channel, etc. What do we have been focusing primarily looking to optical side? Can we leverage the membrane structure, the photonic crystal cavity structure, to make this very compact and optical detection and sensing and platform? So you can see here, basically, so this still, still much, it's still large, but it's much smaller. It's a suitcase kind of structure now here. Is primarily limited by this part of the mechanics here for gas delivery separation. But otherwise, the optical side, that's where I would be focused on here, looking to a few aspects in terms of the photonic crystal sensors and the integration with the column for gas separation. And then in the future, we'll integrate the detectors and of course spectrometers and even sources for a whole integrated optical system for this gas analyzer. So our vision has been, as I mentioned earlier, to have this kind of vertically stacked tandem structure where you have a sensing element, could be photonic crystal structure embedded in the microfluidic channel or the column to be built for the gas separation. Then we have a laser source on top, and of course detector or spectrometer on the bottom to be depend on the configuration of the source and detector. We can then have a fully integrated optical system. In terms of the different sensors, based on high Q resonance structures I already mentioned earlier, we looked into monolayer or single layer structures, not monolayer, single layer PCS photonic crystal slab structures, or bilayer structures for different kind of designs. The goal here is to try to improve sensing performance. We started with liquid sensing here, and we look into polymer coating in photonic crystal cavity for gas sensing. And then finally, we looked into, of course, some of the work was done on this pressure sensor, different configuration for sensor side. And this just summarizes the progress we made over the years already. The principle itself is not very complicated. The challenge probably is the proper design, trade-offs in terms of different lattice configurations for Q and sensitivity, detection limit, etc. So what we have been progressing over the years, starting with the relatively reasonable good performance to further improvement in terms of both the sensitivity, detection limit, and finally, use a bilayer structure to get a very good detection limit by combination with a high Q and a good sensitivity here. So those work already been published in the last few years, and that's the progress we're making in terms of liquid sensing side. So based upon that, then we move into the vapor sensing or gas sensing side. This is very similar to, of course, the polymer coating in the GC system, where Professor Sang is the expert on that regard. So basically, it's kind of thin film coating onto a silicon photonic crystal cavity here. And of course, the tricky part here is the thickness of silicon, the polymer here, because in the conventional tube or the column is very large, tens of microns or centimeter size sometimes. Here we're talking about a kind of really sub-micron features. So one of the challenges we are looking into how to really look into the optimal polymer thickness, where you can see the wavelength shift determined by either the gas absorption induced the index change in the polymer, or the thickness change induced due to the gas absorption here. And the effect is kind of counting towards each other. So you have to kind of play or have a trade-off, depends on which part you're working on, whether it's index changing or thickness changing. Here you can see a different trend in terms of the design here. And also, of course, from design point of view, you have to look into different mode as to how to have a more, for example, mode overlap. In this case, the evanescent field tilt into the polymer region to have a better, more sensitive response. So the design of this, optical field and then the mode extension outside the silicon into the polymer, and then the coupling with the polymer all plays a critical role here in the final design. You can see some of the details here. Here, just show briefly the sensing performance. I think try to wrap up quickly here, where you can see, depend on different polar, non-polar gas. You can see already by using this simple polymer coating, you can actually control or separate different kind of gases with different responsivity here. You can see. And finally, the recent demonstration was basically try to put the sensor into this prefabricated channels, basically all columns. You can see the structure we're making kind of double, spiral structures where to extend the length of the column structure, and then we integrate our photonic crystal slab and sensor, which is again based on the transfer printing process, into this channel here. So then basically we have an integrated column and the gas sensing all on the chip now. Here just shows more images of actual devices. You can see here this column, that's the tiny piece here, that's the PC structure. If you zoom in, that's where the transferred photonic crystal structure being in it's a thin film silicon photonic crystal slab being integrated inside the column here. And the performance is shown here with a reasonably good Q, about 10,000 here for this particular demonstration. And here just shows more result here. You can see we was able to separate and monitor 4 different gases in this case. So it's really depend on, of course, the column design here. So our goal is probably eventually for 10, but at this point, 4 is most cases probably is more than enough already. From some of the practical application point of view, you can see actually this performance is very compatible to commercial instrument here. And also it's pretty fast here because the scaling of the column size and the length also make the whole system faster in terms of detection. So that's basically the progress. I can see there are a few more additional works need to be done, and some of the challenges is integration with light source and spectrometers or onto this platform for the wholly complete optical system. That's some of the things we're still working on now. So finally, just to briefly touch upon the last element for this integrated vertically stacked column system here, where how to have this beam control for focusing, for even steering sometimes, where we have been investigating the so-called flat optics. Any work on optics will know this so-called metamaterials has been pursued by many groups already, where you replace the conventional traditional bulk optics with a thin layer in meta surface structures. It's really very well developed, and lots of progress made already, and with practical applications. There's still some challenges. For example, intrinsic configuration here is not necessarily compatible for flexible structures, because you have these isolated columns here, right? Plus, it's not necessarily mechanically robust, especially for flexible applications. It could be a challenge. Plus, it typically is very tall, and to get a 2-pi phase shift, the column actually is quite tall pillars here. So what do we been looking into? Okay, can we look into the photonic crystal structure here? So indeed, okay, probably we don't have time to go through the details, but what I'm trying to summarize here is indeed, by proper design, we can have this kind of single layer silicon structure sitting on low index material, where here just shows the details about the design criteria. What's the windows of the design, such that you can actually indeed be able to achieve full 2-pi phase tuning by having light passing through this light, either for reflection or for transmission, to achieve 2-pi phase tuning, as well as either high reflection. In this case, 85% probably can be improved further, but that's the number we have now, or 80% of transmission, depends on the operation mode, which one you want to use. So basically now you can see, if we can develop this kind of platform where you can have a 2-pi phase tuning, and then also very sensitive phase tuning, then you can be able to realize either for sensing or actually for beam control for meta lens structures, where you can control the beam shape for integration purpose. And then this could be very robust in terms of integration with a flexible platform. And it's very thin as well. So here's just the summary slide, show some of the key structures we have been developing over the years by leverage the membrane transfer printing process and the photonic crystal cavity for lasers, for filters, for potential detectors, as well as a flexible filter, and then of course optical sensors. And a few key components here is, I say, this one. Inorganic memory does offer this platform for flexible wearable electronics, and photonic crystal structures can be incorporated into both organic and membranes for active devices, detection, emission, modulation, filtering, guiding, sensing. And then hopefully we can be able to achieve a very compact optical gas sensing analysis system by stacking different membrane cavities with different functionalities with a simplified optical integration scheme. That's all. I will acknowledge my students, groups, and funding agencies, fabricating the UTA Nano Research Center here, and also my collaborators, John Rogers, Professor Tian Ma, and Xianhui Fan, and Dr. Sang here. Thank you.
Oh, hi, Weidong. Thank you very much for giving a very inspiring talk. I'm Feng Yan.
Oh, thank you. Hey, have fun.
Well, it's a very nice talk, and I'm very pleased to find that photonic crystal can have so many applications. Here I notice a gas sensor. So you can get very good selectivity, right?
Right, yeah.
So how can you achieve it? Why your photonic crystal is sensitive?
Oh, it's not that's good. It's not really. I guess I can try right through. It's not really determined by the photonic cavity here. It's really determined by this gas column here. So the multiple gas coming in will be separated during the transport process in the column because they have a different absorption time, I guess, in interaction time with the polymers. So then when they release, also they will release at different times. So by the time if we have a multiple gas coming in the inlet here, they will come out in the outlet at different time. So we just monitor different time, different gases, and monitor different kind of peaks. For example, let's time to make here is X here is time here. So each we do calibrations, and each time corresponds to each in a different time gas here.
The transfer time will be different for different gases.
Right. Yeah.
And I also noticed that you have the membrane to be modified on the device. Is it provide selectivity?
Well, I guess the membrane itself depends. Maybe adding some polymer or some material. Maybe I guess intrinsically, if it's pure optically, the photonic crystal structure itself, it doesn't really tell which material which gas it is. It does not have that selectivity. Yeah.
So your device can be very small, right?
Yeah, the device can be very small. That's our goal is try
micrometer.
to.
It's 200 micrometer size, several hundred micrometer size.
The device, eventually the limitation is not about the photonic crystal cavity here. It's really the whole system, the other things, electronics, other things probably. But the cavity itself, yeah, it's a few hundred microns because the column we're making is only a few hundred microns here.
Okay. So my last question is about characterization system. You have this photonic crystal, right? But how can you do the measurement? Is the measurement system also very small?
Right. Yeah. Very good question. Well, as I mentioned earlier, yeah, that's our goal. Actually, we are working in actually with some project now, looking to make it very compact. It's very feasible by. At this point, no, we are using a lab testing setup here. So we have a tunable laser, is a benchtop setup. So that's kind of separate from this sensing system here. Yeah.
So there are some micro laser, very small size laser.
Eventually, yeah, definitely. Some of the technology is there. For example, some of the lasers we are developing, or some of the commercial lasers, for example, VCSEL itself can be very small, right? A few, tens of microns in thickness. If we remove the substrate, same thing, a few tens of microns in lateral dimension. So you can make those devices very small. And the one we are making is a few micron thick. So even thinner actually, with a few maybe 10 micron or also like lateral dimension. Yeah, it can be very small structures. Yes.